internal energy is a concept that you may not have been properly introduced to before. And I want to take a step back. We're just considering again that example of the box sitting on the edge of the cliff that we looked at in a previous video. So there's our box. And if we give that box a nudge and it falls off the edge of the cliff and ends up at the bottom. Now at the top of that path, the box has a lot of potential energy, but it has zero kinetic energy. So maximum potential energy and zero kinetic. And just before it hits the bottom, when it's traveling really fast, it of course has maximum kinetic energy and zero potential energy. Now just after it hits the ground, it looks like a big mess. And of course it has no kinetic and no potential energy. So where has all that energy gone? It kind of disappeared, as that would violate the law of conservation of energy. And of course you have this intuitive understanding that the box's energy is now being stored as another type of energy. And most of that in this situation would be internal energy. And that's what we're going to define in a bit more detail. In order to understand this new storage mode of energy, which it's not actually a new storage mode, but we'll get to that in a moment, we need to make a really important distinction between macroscopic motion and microscopic motion. So macroscopic motion is the motion of the object as a whole, whereas microscopic motion is the motion of the particles within that object. So when that object hits the ground, the macroscopic motion ceases. It's not moving anymore, so it actually doesn't have any more macroscopic, if you like, kinetic energy. So what we have instead is an increase in the microscopic motion. And what this looks like is the atoms in both the box and in the ground that it hits are vibrating or moving more rapidly. And so we've got a transfer of macroscopic kinetic energy into microscopic kinetic energy. Now, of course, it's not quite as simple even as this. Microscopic energy or internal energy comes in two different forms. So just write this equation out here. Internal energy is made up of microscopic kinetic energy and microscopic potential energy. So this thing here, this internal energy, is made up of your kinetic energy that we were talking about before. So the vibration of atoms, the rotation of molecules, and also I'll just write here, translational motion of the atoms and the molecules inside, not only the remnants of the box, but also in the surroundings of that. But we also have microscopic potential energy, and the potential energy is associated with those kind of spring-like bonds between the atoms. So the bonds that hold the whole thing together can get stretched, and that actually adds potential energy to the system internally. Just like a spring, if you stretch it or compress it, will change its potential energy. The same thing happens with those bonds between atoms. And I've just got a little picture here of those bonds in the atoms. So we've got the motion of those atoms, which is the kinetic energy inside, so the internal kinetic energy. And we've got those kind of bonds there with the little springs between them, which is that represents the potential energy. Now, we can't see visually microscopic motion, but we can detect the kinetic part of it, the microscopic kinetic energy part of it, as with a thermometer. It represents its temperature, and we're going to get to that later on. Now, you may see internal energy referred to as thermal energy, but I find, and some people try and avoid that term, and I'm one of them, because thermal energy implies that it's just about that temperature part of it. And so I like to use the term internal energy, which encompasses both the microscopic, kinetic, and potential energies that make it up. And just a final point, internal energy isn't a special new type of energy. As you can see, it is made up of those two main types of energy that those two main storage forms of energy that we saw before. It's made up of kinetic and potential.